Bismillahirrahmanirrahim. Hello students, welcome to the Electrical Engineering channel. Today I am going to start the fourth chapter of the Engineering Electromagnetics textbook written by William Haight and John A. Buck. And the title of this chapter is Energy and Potential, and we will discuss energy and potential or voltage in this chapter. The energy can be defined as the dot product of force and displacement. In electrostatics, we will use electrostatic force, which is F equal to Q. Q is the magnitude of charge. E is the electric field intensity. Force and electric field are vector quantities. Charge is a scalar quantity. And in calculating the energy or work, we have to evaluate the component of force in the direction of the displacement. So F will be equal to F dot AL, and F is equal to QE, so this will be equal to QE dot AL, and this is the component of electrostatic force in the direction of the displacement, and the force required to overcome the electrostatic force is equal and opposite. So applied force will be equal to minus QE dot AL, and expenditure of energy is equal to differential work done by external source to move Q, and dW is the actually differential amount of work, and that is equal to minus QE dot AL multiplied by DL, because work or energy is equal to F dot DL. So this is F, and here we have DL. DL is the differential amount of displacement, and DL is equal to DL AL. DL is also a vector quantity because it is a displacement, and it is equal to the magnitude of the differential displacement multiplied by the unit vector in the direction of displacement, and dW can be written as minus QE dot DL. So the total work done in moving a charge from initial position to the final position will be evaluated by taking the integral of this expression. So W is equal to minus QE dot DL, and its integral from initial to the final position. Now we will discuss the general concept of work in physics, not in electrostatics, but in uh, translational motion. Right, so work is equal to force along the displacement multiplied by the displacement. So if we have an object which is shown over here, and we are exerting a force F in this direction, inclined direction, that object will undergo some displacement in the horizontal direction clearly, because we are pulling this object by means of a rope. So the amount of work done in this case will be equal to the dot product of component of force in the direction of displacement and the displacement, right? So this force has two components. This is the horizontal component, or F cos theta. This is F sin theta. Now F cos theta is the component of force which is along L. So the work will be equal to F cos theta multiplied by L, and it can be written as F dot L. So F sin theta component is wasted since it is not responsible for displacement along L. This F sin theta component is actually the perpendicular component of force, and since this object is moving in this direction, horizontal direction, so this component is wasted because there is no displacement of this object in the direction of this vertical component. So if F and L are in the same direction, theta will be equal to 0 and work will be maximum. So clearly, if we are pulling this object by means of a rope in this direction, then the displacement will be L, and we will need less force in this case to cause the same amount of displacement. So in this case, a small amount of force will be responsible for the equal amount of the work as we did for in the previous case. So in this case, theta will be equal to 0 and work will be maximum. So if force is applied perpendicular to L, theta will be equal to 90 degree and work will be 0 since there is no displacement along L. So clearly, if we are exerting force and the displacement is in this direction there, then the angle between the force and displacement is 90 degree and work done will be equal to 0. Now we will solve an example to get a deeper insight into the concept of work. So we are given an electric field expression in this example, and we have to calculate the differential amount of work. The magnitude of charge is 6 nanocoulomb, and this force actually causing a magnitude of the displacement of 2 micrometers starting at this point, and the direction of this displacement is also given over here. So we can easily evaluate the displacement vector, which is equal to this magnitude multiplied by this unit vector. So W is equal to minus Q E dot L, and first we have to calculate the electric field intensity at this point. So E at P can be easily evaluated by inserting these coordinates x, y, and z in this expression. So this is E at P, and W will be equal to minus Q E dot dl. Q is also given, E is also given, and dot L is also given. So this dot product can be easily evaluated, and this is the final answer, which is minus 149.3 femtojoule. Now I will discuss the line integral, because we are evaluating line integral in evaluating the work or energy. So suppose we are given 2 points. First initial point is B, final point is A, and we are moving a charge starting from point B up to point A in discrete steps. So the length of single step is delta L. The length of this first step is delta L1. The length of this second step is delta L2, and clearly these displacement vectors are incremental displacement vectors, and the direction of electric field intensity is also given, which is from left to right. So this is the direction of the electric field intensity EL1, EL2, and EL3, and so on. So W is equal to minus Q E L into dl from initial to the final position. So W can be written as minus Q EL1 delta L1. This is delta L1, and we have to multiply the component of electric field in the direction of delta L1, so that will be EL1. Similarly, EL2 multiplied by delta L2. Similarly, EL4 multiplied by delta L4, and so on. And the final value is EL8 delta L8. Now we have the component of electric field in the direction of displacement or incremental displacement delta L1. So EL1 into delta L1 will be equal to E1 dot delta L1. Similarly, this will be E2 dot delta L2 plus so on plus E8 dot delta L8. If the electric field intensity uh, all along the way is uniform and is equal to E, then we can write minus Q E dot LBA. So E1 will be equal to E2, and all these electric field will be equal to E, and there will be dot product, and the sum of these incremental displacements delta L1 plus delta L2 will be equal to LBA. So this thing can be written as minus Q integral from B to A E dot dl. In Cartesian components, dl will be equal to dx ax plus dy ay plus dz az. Similarly, in cylindrical components, dl is given over here, and in spherical components, dl is also given over here. And if we have a line charge distribution, then electric field intensity will be equal to rho L over 2 by epsilon rho A rho. And if we are moving this charge along the phi direction, right? This is the direction of phi. Then dl will be equal to rho d phi a phi, and E is equal to rho L over 2 by epsilon rho A rho. This is the electric field due to a line charge distribution, and work in this case can be evaluated, and that will be equal to minus Q E dot dl. So E is equal to this component, which is the rho component. Dl is actually along the phi direction, so A rho dot A phi will be equal to 0. So in this case, the total work done will be equal to 0, because the dot product of A rho and A phi is equal to 0. Now, if we are moving the charge in the rho direction from this point A to B, then dl will be equal to d rho A rho, right? Because if dl is d phi, then we will have only this component, and if we are moving the charge in the rho direction, then dl will be equal to d rho A rho. So again, we can evaluate the dot product of electric field and dl. So minus QE dot dl will be equal to this expression, and this can be written as minus q rho L over 2 by epsilon ln rho, and this will be equal to ln A over B, because we have a negative sign over here. So here it will be ln B over A, but this negative sign can be made as the power of this argument of the natural log, so it will become A over B. So that is all about the mathematical formulation and physical explanation of work and energy and line integral. I hope you have understood these concepts of work and energy in the electrostatic fields. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.